In this video, we cover learning outcome number 4, which is all about summarizing important terminology related to correlation and regression. We're going to talk much more about correlation and regression with more depth in Chapter 10 after we've studied hypothesis testing. So remember, Section 2.4 or Lesson 2.4 is just about getting a qualitative understanding of correlation and regression, and then looking at some rules of thumb related to technological output that will allow us to determine whether or not we have a evidence of a correlation between the variables. Now, at this point in our study of statistics, we really don't have the mathematical background to explain why these rules are what they are, but we will have a much better understanding of why we're doing what we're doing when we get to Chapter 9 on hypothesis testing, and when we talk about correlation and regression again in Chapter 10. So in this learning outcome, we're just going to review all of the important terminology, and then finally we're going to introduce this term of linear regression and talk about what that means. So let's start by reviewing some important terms. The first important term is scatterplot, also known as a scatter diagram. This is just a graph of paired quantitative data. When you look at it, it's just a bunch of points in the XY plane. Now, correlation is a relationship between two variables. Often we create a scatter plot to see if there seems to be a relationship between the two variables. Now, there could be many different types of relationships between the variables as exhibited in our scatter plot or scatter diagram, but we're often interested in if there is a linear correlation, between the two variables. So that means as one variable goes up, the other one goes up, or as one variable goes down, the other one goes down, and they go up or down in a linear fashion. So you would say that a line would really fit through the data, and that line could be used to predict y values given certain x values if there was a linear correlation between the two variables. Now, when we're looking at scatter plots, we're just saying, just by looking at it, we're like, yeah, that looks kind of like a line would fit through that, and that makes sense. It seems like when one goes up, the other one goes up, or when one variable goes up, the other one goes down. But we'd like to be able to measure that. We're going to talk more about where these numbers come from, but two numbers that allow us to measure that strength of the linear correlation between variables are the linear correlation coefficient R and what are called p-values. Now, the linear correlation coefficient R is a number between -1 and 1 inclusive, measuring the strength of the linear relationship between the two variables. So if R is equal to 1, that means all of the data points in our data set would lie on a line, and that line would have a positive slope. If R is equal to -1, that means all of our data points would lie on a line, and that line has a negative slope. Now, if R is close to -1, but it's not -1, or if it's close to 1, but it's not 1, then we would say that we have evidence of a linear correlation between the two variables. Now, when I say close, you should probably ask, what do I mean by close? And we'll talk about what we mean by close in a little bit, but it has to do with those critical values that we discussed a couple of videos back. So this is a number that measures the strength of that linear relationship between variables. If the absolute value of R is 1, there's a perfect linear relationship. And if R is close to 1 or -1, then there is a trend towards a linear relationship. As one variable goes up, the other one tends to go up. And as one variable goes down, the other one tends to go down. Now, if R is near 0 or equal to 0, then there is no correlation, no linear correlation between the variables. That means the points are going to be all over the place in your scatter plot. Now, another way to measure or determine whether or not you have a linear correlation is to look at the p-value. Now, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data, provided that there's no relationship between the two variables. So that means if p-values are small, that means the probability is small. And if the probability is small, that suggests that there's evidence of a linear correlation. If the probability is large, that we'd have an R value that was that size or larger, well, then we'd say, this might just be due to chance, so we don't have evidence of a linear correlation. Now, linear regression is our last term, and linear regression is the process of finding that straight line that best fits through our scatter plot of data. So we're going to have a collection of paired sample data. Given that, we can come up with what's called the regression line, or the line of best fit, or the least squares line. This is the straight line that best fits the scatter plot of data. A lot of students get confused between correlation and regression. Correlation is about whether or not there is a linear relationship. Regression is about finding the equation of that line. So this is our regression equation. The symbols look a little different. It's just like y equals mx plus b, but we're using slightly different symbols, which we'll talk about more in chapter 10. But this is a regression equation. We use this y hat to represent the y value that's predicted by this regression equation. Instead of y equals mx plus b, we have y hat equals b sub 1 times x. So b sub 1 is the slope of that regression line, plus b naught, or b sub 0, and b naught, or b sub 0, is the y-intercept of that regression line. It's just another form of y equals mx plus b. It's the same thing. We just use different letters and y hat because of some history, and we use this y hat because it's a predicted value of y and not an actual value of y in one of our ordered pairs. Here's an example of a regression line. This was created by technology. So we've got our shoe print length and our heights for 40 data points. I believe we showed earlier that there was evidence of a correlation between these two variables when we had n equals 40, when we had 40 data points. So given that data set, we used technology to come up with the equation of the regression line, and then we graphed it, and that's exactly what it looks like. So here's some StatDisk results. Notice you've got your correlation coefficient at the top, then your critical values, and then your p-value. All of that tells you whether or not there is a correlation. Now, in the second part of the StatDisk output, you have regression results. So that's telling you if there is a linear relationship between x and y, this is the best fit line that fits that data. The y-intercept is given by b naught, or they're using b0, and it turns out to be 80.9 approximately. And the slope is represented by b1, and that turns out to be 3.22 approximately. So the general form of the regression equation has a y-intercept of this value and a slope of this value. So you put those two pieces together, and then you've got the equation of the regression line, which is this. So that y hat, that represents a predicted output. So look at our scatter plot again. You've got shoe print length on the x-axis, and you've got height on the y-axis. So if someone says, I've got a shoe print length of approximately 30 centimeters, what height would you expect a person with a shoe print length of 30 centimeters to have? What height would you expect given this data set? Well, you could plug in that x value, x equals 30 centimeters, into this equation, and you would get the y value that is on that graph at x equals 30. So it's not the y values that are actually plotted in that scatter plot, but that's going to be the y value on the line. And it looks like the y value on the line when the shoe print length is 30 centimeters is approximately 179 centimeters of height. So somebody with a shoe print length of 30 centimeters tends to be about 179, I guess, centimeters tall? I don't know. Anyway, I'm tired. But that's the height that goes with that shoe print length. Now, using variable names, the equation is this. The height is 80.9 plus 3.32 times the shoe print length. So you take the length, you multiply by this slope, and then you add that 80.9, and that's going to give you the height back of that person. So we're going to talk more about how to find the y-intercept and the slope when we talk about a regression in chapter 10, but regression and correlation are different. Correlation is all about whether or not there is a relationship. Regression is about finding the equation of that line given the fact that there is a relationship. So we'll talk more about this in chapter 10, and that is the end of our lessons over chapter 2, which is all about visualizing data.